of non-processed elements in the bleaching conditions of eucalyptus kraft pulp. Wood until obtained bleached pulp. Besides pulp, this process also recovers several chemicals, namely sodium and calcium, produce energy, and of course release some gases, liquid and waste emissions to the environment. This work is mainly related with the bleaching area, here highlighted, and this area has the objective to obtain a white bleached pulp at the end. The water consumption in the pulp industry is a critical aspect. Currently, the consumption in most of the industrial mills are in the range of 25 to 50 cubic meters per ton. However, some very updated industries were able to reduce about 80% the consumption and reach an impressive mark of nearly 20 cubic meters per ton. The water consumption in this type of processes is mainly due to caulking, washing and bleaching. Indeed, bleaching is responsible for a consumption between 40 and 60% of water. This reduction of 80% of course has a very important impact, reducing the emissions to the environment. Here I present a washing stage. This is a possibility, there are many others, and in this case the brown pulp will be bleached in a sequence that involves oxygen, then chlorine dioxide, followed by an alkaline extraction, and finally 2 stages of chlorine dioxide. The washing is implemented in a countercurrent flow, and then at the end it is produced 2 types of effluents, an alkaline effluent and an acid effluent. The non-processed elements is the main point of our work, and those elements correspond to the ones that do not actively participate in the pulping process. We are talking about calcium, magnesium, potassium and so on. The main sources of these elements are wood, chemical products and fresh water. What is the consequence of decrease the water consumption? The main consequence is increased accumulation non-processed elements in the industry, and because of that inorganic deposits are formed. These deposits leads to corrosion and formation of scale deposits in the process. So, the objective of this work is to study the behavior of calcium as an example of a non-processed element, namely the partition between the fibers and the liquid phase through adsorption processes under different bleaching operated conditions. In the future, this equilibrium data will be integrated in the software, the WinGEMS, which needs some improvement in the databases. Regarding the adsorption experiments, we tested 5 variables, namely pH in the range 2 to 10, calcium concentration in the range 500 to 3000 milligrams per kilogram of pulp, the type of pulp, PO2 and D2, which will be explained in the following slides, the effect of temperature, and the ionic strength where the calcium is present. The mixing speed is 80 RPM. Consistency of the suspension is 5% and contact time is 16 hours. The tests involved to put the suspension in the shaker during these conditions. At the end, we performed a filtration to separate the fibers from the liquid. The non-processed elements are present in the liquid, and these elements will be quantified through atomic absorption spectroscopy. The collected samples, we take more than these ones, but the work focuses mainly in these 2 samples. The first one corresponds to the pre-delinified sampled with oxygen, and the second sample corresponds to a fully bleached sample. In our work, some data also were gathered to the brown stock washing the pulp. Regarding the results and discussion, first of all, we were considered about the determination of functional groups in the pulp, namely carboxylic groups. And why is that? Because for simplicity we consider that the carboxylic groups are the ones that can interact with the metals in solution. So several equilibriums can take place, but this one is the most important one. The carboxylic acids can be deprotonated, and the negative charge can interact with the metals. To calculate the number of active sites, we perform some automatic titrations with sodium hydroxide in a suspension of 1% plus sodium chloride and chloride acid. The titration curves are shown in this graph as a function of the volume of sodium hydroxide added. The green curve corresponds to the blank test. The blue corresponds to the most bleached sample, and the PO2 sample corresponds to the orange curve. Here it is possible to see that more volume of sodium hydroxide means that more active sites are present in the pulp. From this data, it was possible to obtain the numbers that are summarized here in this table, and we can see that the number of functional groups decrease as the pulp becomes more bleached, and the number of active sites varied from about 100 for PO2 pulp and 26 for the pulp D2. It was possible to obtain the equilibrium constants, and with that to obtain the pKa values that correspond to the equilibrium data. In respect to the effect of calcium concentration, in these graphs I present you the adsorption capacity of calcium as a function of pH in the suspension. The graph from the left is related with the pulp PO2 and the right to the pulp D2, and the adsorption observed for a lower level and a higher level of calcium is indicated in the graphs. It is possible to conclude that as calcium concentration increased, the adsorption capacity also increased, and the behavior is similar to both pulps. Regarding the effect of calcium concentration, in these graphs it is possible to see that as the concentration of calcium increased, the adsorption capacity also increased, but the most important aspect is that as pH increased, the adsorption capacity also increased. And this is a very important point because in the simulator this aspect is not very well taken into account. So this data will be very relevant for future simulations. In respect to the effect of temperature, these graphs clearly shows that this is not a very important variable in our system. Indeed, this is observed even for lower calcium concentrations or for upper calcium concentrations in the suspension. Next, the effect of the type of the pulp. These results are not very satisfactory in our point of view, because here, although we have determined a different amount of active sites in the pulp PO2 and D2, the adsorption capacity seems similar, and similar for both the lower level and the upper level of the calcium concentration. So in our opinion, these experiments must be repeated in the future. Finally, the effect of ionic strength is an important aspect, because the species are in a solution, in a very complex solution with a lot of other elements. Here we tested two levels of ionic strength, and as you can see, as the ionic strength increases, the adsorption capacity decreases. So this aspect must be taken into account in the simulations. Finally, as the main conclusions of our work, it is possible to calculate the carboxylic groups by titration, and this is the range obtained from 140 to 26 millimole of active sites per kilogram. And regarding the adsorption experiments, you can see that the pH is a very important variable. The calcium concentration influences the adsorption capacity. The temperature is not an important variable. Both pulps show similar adsorption capacity, but these results must be repeated, and the calcium adsorption capacity decreases with increase of ionic strength. The obtained data were well modeled by the Donan equilibrium. These results were not shown in this presentation, and they will be integrated in the databases of the software MinGEMS that is commonly used in the pulp and paper industry. I want to acknowledge the Impactus project and say thank you for your attention.
Hello, welcome to my session, everyone. My name is Cláudia Esteves and I work in the Research Institute of Sweden, known as RISE, together with my PhD supervisor, Elisabeth Brandvall. The work that I will present today is also done together with Olena Svestianova and Søren Ostlund from the Royal Institute of Technology in Stockholm. The title of my presentation is Process Modifications in Cooking and Oxygen Delignification. Those are the facilities where this work was performed, located in Stockholm and known as STFI or Inventia in the past. The work was done in the pulp, paper and packaging department. I will briefly talk about two different types of impregnation. Why did we choose oxygen delignification for this work? I will go through our methodology, our results, and then the conclusions. The purpose of this study was to evaluate and compare oxygen delignification performed after a craft cooking done with two different types of impregnation: a standard impregnation and a high alkali impregnation. The impregnation step occurs to facilitate the transport and the diffusion of the craft chemicals inside the wood chips. So the better the impregnation, the better and more efficient will be the craft cooking. It's crucial to have an homogeneous concentration inside the wood chips in order to not affect the pulp quality. And the main point of craft cook is to remove lignin without carbohydrate degradation. So it's possible to improve impregnation and therefore improve craft cooking. Previous studies done by Elisabeth Brandvall showed that we can get around 1 to 1.5% of yield improvement when we perform a craft done with a high alkali impregnation instead of a standard impregnation. With this high alkali impregnation, we will get a faster diffusion rate and a faster removal of acetyl groups. We will compare these two types of impregnations together with oxygen delignification. And why did we choose oxygen delignification? First, because increases fiber charges. And this increase in fiber charges will improve some of the properties that I will show you later in this presentation. The picture that I have here is a representation of uncooked wood that has a lot of fiber charges because it has a lot of lignin and carbohydrates that are where the fiber charges are located. When we start performing a craft cook to get a lower kappa number, we are mainly removing lignin and therefore we are losing fiber charges. A way to preserve this is to perform a shorter craft cook and then perform an oxygen delignification. In this case, we can increase fiber charges by lignin and carbohydrate oxidation. So, we have the same lignin content, but we have much higher fiber charges in the sample performed with oxygen delignification. And this will result in a more swollen fiber. So this increase will lead to a higher swellability of the fiber that will help the refinability and therefore it will increase the paper strength. The raw material that we used was softwood chips, a mixture of spruce and pine. They were screened and hand-picked. I will present now the methodology, making a note that the black lines will always represent the trials done with the standard impregnation and the yellow lines performed with a high alkali impregnation. So we performed two different craft cooks, two different kappa numbers. So in the picture that you have arrows, you can see a standard craft cook performed to kappa 27 and a high alkali impregnation cook performed to kappa 28. And then we performed shorter craft cooks to kappa around 50, and then we did oxygen delignification to the same kappa number as the other two. And this way we can compare first the difference that we have between getting a lower kappa number from just a craft cook or a craft cook done together with oxygen delignification. And then we can compare the two processes done with a standard impregnation and with a high alkyl impregnation. We analyze the kappa number, the fiber charges, and also the morphology of the fibers in these different steps. Then we performed refining to different levels. We studied the water retention value, superregular degree, and also the morphology along these different refining degrees. Finally, we did lab sheets to study and evaluate the tensile strength. The craft process. So, like I said, the difference is in the impregnation step. So for a standard impregnation, we have a standard concentration of the chemicals. We introduce this white liquor inside the digester, and then we perform the impregnation during 30 minutes. After that time, we'll increase the temperature and we will start the cooking step. For the high alkyl impregnation, we start with a much higher concentration of the chemicals. And after the same 30 minutes, what we will do is remove all the impregnation liquor that we have inside. We will do a titration to see how much is the concentration that we have after the impregnation. And then we will make a dilution with the impregnation liquor and water to get around 0.5 molar of hydroxyl groups for the cooking step. And then we do the same. We increase temperature and we start the cooking step. That will take less time than the other one. The oxygen delignification was much simple. So we used autoclaves coated with Teflon with these conditions. Now I'll go to the results part. And I will start by looking at the yield improvement. So like Renval has seen, we also got around 1% of yield improvement when we compare a standard impregnation and a high alkyl impregnation. When we look at the oxygen delignification step, we can increase the yield about 1.2%. Of course, this will lead to some savings. So first, we can have around 2% of wood savings by performing a high alkyl impregnation instead of a standard impregnation. And then 3% if we use oxygen delignification for the same kappa number. This will result around €1 million per year of cost savings. That is an important conclusion to take from here. Now going to the fiber charges, like I said, we start with a higher kappa number with a lot of fiber charges because we have a lot of lignin. But then we start performing the craft cook, and we are decreasing the kappa number and losing fiber charges. And this loss is about 30 to 40%. Then when we perform an oxygen delignification, we can increase these fiber charges around 15 to 80%. And the most important is when we compare for the same kappa number. We have an increase in fiber charges around 90 to 70% when we perform an oxygen delignification. And this will be important. Why this is important? Because by increasing fiber charges, we will increase the water retention value and the swelling of the fiber. So in the graph in the left, you have the water retention value along the beating. So for the oxygen, we get a more swollen fiber in comparison with the craft cook. This will help in the refining process because the fiber is swollen, so it will get more fibrillated, and therefore it will result in a better conformation and stronger paper. The graphs in the right are the Chopper regular degree along beating and tensile index. So at the first sight, we can see that we increase Chopper regular. That maybe is not so good for the runnability of the paper machine. But when we look in the graph down, we have the same tensile and the same Chopper, but with lower refining degree. So this is a good thing. Looking at the tensile index, we can see that oxygen lignification presents better results for the strength. So we have two graphs, one along beating and the other one along density. For the same density and for the same tensile, is possible to observe that oxygen lignification needs only 2000 revolutions, while the craft cooked pulps need 4000 revolutions. This is mainly due to the water swellability of the fiber, like I said before. So by increasing the swelling of the fiber in the beating process, we will improve the fibrillation, and therefore we will have a better conformation that will result in a better strength. And if we want to see in terms of energy savings, by doing this, we get around 55% of less refining energy. If we want to see for the same refining degree, like 4000 revolutions, we have an improvement about 18 to 10% in the tensile strength. So this is an important conclusion also to take from here and to take from oxygen lignification and by the improvement of the fiber charges. To finalize, we'll also study the fiber morphology. So the graphs represent the curl index, that is the deformation degree that we have in the fibers. For the oxygen samples, we have a slightly decrease or no difference at all in the refining process. However, for the kraft pulps, we have an increase, especially when we look for the high kappa number pulps. And this is mainly first because we have higher lignin content, so the fiber is more rigid, is stiffer, so in the refining it can be more damaged instead of when we see the oxygen fibers that are more swollen, the refining process is not so aggressive. So this was just an interesting conclusion and observation that we realize in this study. So, as an overall conclusion, we saw the same as was previously seen. High alkali impregnation can give us around 1% of yield improvement. Oxygen lignification, when we compare to the same kappa number, can give around 1.2%. And in overall, for all the results, we get an increase in fiber charges when we use oxygen lignification, and this will lead to a fiber increase in fiber swelling that helps in the refining processes. So we will get a stronger paper in the end. And then this will result in energy savings by first reducing the craft cook step, then by increasing the yield with the high alkali impregnation or by oxygen, and then increasing the tensile index with lower refining energy. Those are our references, and if you have any questions, please feel free to contact me. And thank you very much for your attention. Muito obrigada.
Hi everyone, my name is Anna and this is my first time here in Tecnicelpa and I'm really excited about it. Before I start, I would like to say that I hope that you and your family are safe. So, starting with the presentation, this work was developed in the University of Aveiro and is linked to the project Impact. The theme of this work It is the development of models, in this case, multiple linear regression models, to predict absorption and also the capillarity of Eucalyptus globulus tissue pulps. In the industry of tissue, the absorption and capillarity are highly important. Because imagine if we are talking about facial or hygienic applications, the values allowed for each one of it will be different. So we need all the time to have those values. In the case of absorption, we are talking about the capability of water absorption in predefined conditions. And if we are talking about the capillarity, we are talking about the level which a liquid elevated in a paper stripe. They are controlled by different properties. In the case of absorption, we are talking about fiber structure, mainly the empty spaces in material. However, if we are talking about capillarity, it is a little bit different. We are talking mostly about the capillaries between the fibers, the ratios of the pores, and also the contact angle formed between the liquid and the surface. Besides of it, both of them are controlled by carboxylic groups and also hemicelluloses in the fibers. To determine such values in the lab, this could be quite time consuming. We need to produce papers, and you need a proper equipment, you need a lot of pulp, you need a lot of time, and after that, you need to have equipment appropriated to determine the values according to the ISOs. So if we are talking about absorption, we need to use what we call the basket method. And if we are talking about capillarity, we need to use the Clem test. Okay, so our idea is to forget this equipment and the necessity of to produce tissue papers and build models that will give us the values very quickly, only using the data from the fiber test. And we don't know, but we will see if we need also the data from the pentosanes and also the carboxylic acids. And I know that in this moment, if you work in the tissue area, you are putting a big question mark right now, because maybe you are saying, okay, but pentosanes and also carboxylic acids could be also time consuming. Yes, I know, and you are right. But here I will say that we have a big difference, at least in my point of view, because we don't need a specific lab, okay? And besides of it, and we will see further during the presentation, we don't know yet if we need this data or not. However, and take into account what I present to you, we believe that these parameters influence the absorption and also the capillarity. So we need to see, at least when we are developing models, the importance of it or not. Okay, so to build the models, we use a software, a statistic one, whose name it is SPSS, and we select a tool where is the name it is stepwise multiple linear regression. And with this tool, what we pretend is to build a model, as I said before, but we will start with a large number of predictors, the fiber test data, the pentosanes, carboxylic acids as well, and then we will try to select a small subset of data. I show to you how it works. We use the backward elimination. So we start with 5 imagined variables, and then we will remove time after time variables that are less significant for the model, and we will stop until reaching the stopping rule. So we can start with 10 variables, imagine, and at the end we will have 2, or we can start with 10 and at the end we will finish with 8, imagine. It will the software that will tell us what is important or not for the model. To build our model, we also need two types of data. We need one for develop the model, and we will need another one for the model validation. And this is very important. If you are trying to build a model, you don't need just data for the develop. We also need data for the validation of it. In this case, we have 25 samples of Eucalyptus globus pulps with different cookings and bleaching histories. It is also important because we are not talking about always the same sample or the same type of sample, because our idea is to build a model with a large range of properties and that could work for different type of pulps. Because as you can see here, we have pulps with a value of carboxylic acids of 2.6, or we also have pulps with a value of almost 12. So they are different samples with different properties, as I said, with different cookings and different bleaching. So our idea is to build models that we call it robust, okay? Not just for you in a specific type of application. We can that these models works for every type of Eucalyptus globus. So, showing to you the models that we develop, and when we are talking about models, the first thing that we need to look and to see, it is the coefficient of determination and also the multiple coefficient of determination. This word could be quite tricky. So the value, the maximum value is always what we are looking for. And in this case of absorption, we achieve almost a value of 0.90. And also in the case of the capillary, we also achieve the value of 0.90. So just for you to have one idea, here in the case of absorption, it is important to see and to call your attention that we don't need anymore the values of carboxylic groups and also the pentosanes. So it is quite interesting because we only need data of the fiber test. So it will be very quickly to have the values. And in the case of the capillarity, it will be necessary the results of carboxylic groups. Regarding the model evaluation, we have here, I will say, very interesting results, because in the case of absorption, we are talking about a model deviation of 0.6. And if we look for the standards and what they say in the standards, they achieve or they consider values between 0.2 and 3.5 when they are talking about the deviations between the values. In the case of the capillarity, we are talking about values of 2 millimeters. And I don't know if you did the test already, but I will say honestly that only the human error could be or should be higher than 2 for sure. Okay, so I will say that we have models very, very robust. Besides the models that we built, we also develop software. In this case, we use Visual Basic. This is in Portuguese, but I explain to you, and I have in the next slide a video showing you how this software works. So, our idea is to build a software that can be used in a lab, in the industry, all over the place. And you only need to put the data of the fiber test, and you will have in a fast way the values of models. And more than that, at the beginning, you can compare the values that you are achieving with the models with the values that you are achieving in the lab, in the industry. I know this could be quite important, but because imagine that you are buying the software and the models, but for sure in the first month, I will say you need and you want to compare the values of the model with the models of the values that you are achieving in the lab. So with this software you can do it, and besides of it, it will appear in a red color I showed to you if the values are very different from those that you are expecting for. Okay, so here I have an example how it works. Is in Excel, so you click in calculator, that means calculated. You will put all the values, coarseness, curl, kink, etc. Then in the next boxes, you will put the values of the what I call it internal methods. That is the values that you have in your own lab, not from the models. You'll put all the information related with the bulb. You put calculated, you get out of the big box, and it will show to you the results. And as I said before, it will appear at red if the values that you achieve are very different, because just for you to have an idea here, you have that, for example, you have a value of -6 for the absorption, but you know that the internal methods, the value is 9. So the color, it will appear red, so don't consider it. So as the final conclusions of the work, I will say that the main goal was the development of models that allows the determination of absorption and also capillarity in a fast and accurate way. We use 25 samples of eucalyptus globus craft pulps with different cooking and also bleaching histories. We use the SPSS software, and to build our models, we use the tool multiple linear regression with the backward elimination technique. For the absorption, the model includes coarseness, fine, kink, and curl. And in the case of the capillarity, we are talking about coarseness, fine, kink, curl, and also carboxylic groups. Finally, and additionally, a prototype of software was developed in the Visual Basic, and that could be applied in the industry. Thank you very much for your time. I hope you like this presentation, and please be free to do any question that you may have.
Hello, my name is Gloria Ngene. I am a PhD student of the Grenoble Institute of Technology, Pagora, affiliated with the University Grenoble-Alpes. I'll be presenting a part of my thesis entitled Effect of Valley Beta Refining on Hemicellulose Extraction from Hardwood Paper Pulp. This project is supervised by Professor Jean-Claude Roux and Professor Dominique Lachnan. I do my research work at the Laboratory of Pulp, Paper Science and Graphic Arts in Grenoble, France. Plant fibers are a major source of cellulose. In fact, they are the most abundant and important source of cellulose. Cotton produces the purest form of cellulose with purity of about 90%, but over the years, there has been decline in cultivation due to high irrigation demands, competition with land for food, and other challenges. Other sources of cellulose include wood, bamboo, and agricultural residues. But of these sources, wood is the most important, as over 70% of the global dissolving pulp production is sourced from woody biomass, and the challenges associated with cotton are not associated with wood cultivation. Applications of cellulose include paper making, and paper is usually applied in print media, but over the years, due to the popularity of the electronic media, the demand has been declining. Paper boards are also produced from cellulose, and they are used for packaging materials. Also, another application is dissolving pulp. Dissolving pulp is usually produced via the acid sulfide process or the pre-hydrolysis craft process, and they are then used for production of biodegradable biomaterials. And the demand for these products has been increasing over the years. Paper pulp has a cellulose purity of about 70 to 80% and hemicellulose of about 20 to 25%. And since its typical application has been declining, it can serve as a viable feedstock for the production of dissolving pulp. And if the cold caustic extraction process is used for this process, and if the feedstock, like in the case of this study, is hardwood, then the xylene extracted from this process of upgrading the paper pulp to dissolving pulp is recovered in the polymeric form, which has applications in a coat and film making. And another incentive for the upgrading of paper pulp to dissolving pulp via the cold caustic extraction is that the additional digester capacity required in the pre-hydrolysis process is not required here. And also there is this process facilitates the chemical recovery system, since there's no problem of pH control like we observe with the pre-hydrolysis craft process. The objective of this project is to investigate the impact of valley beta refining to the hemicellulose extraction from paper pulp. Here we have a table presenting the characteristics or property of the pulp, paper pulp and the dissolving pulp. In the course of the study, we'll be looking at reducing or removing the residual hemicellulose content down to about 5% that's required for dissolving pulp, and we'll also be controlling the molecular weight distribution. Processes of hemicellulose removal include alkaline, acid, ionic, and enzymatic extraction, but due to the recalcitrant nature of cellulose, its complex structure that is resistant to chemical and enzymatic agents, these processes alone are not able to efficiently remove the hemicellulose. And so they are usually combined with mechanical treatment or enzymatic treatment. So this mechanical or enzymatic treatment could be a pre-treatment or a post-treatment. And so coupling the two treatments improves the extraction of the hemicellulose from the paper pulp. In this context, when we talk about refining, we mean mechanical treatment that is applied to pulp to induce modification of the fibers. And this figure represents the mechanism of the refining process. So it starts with the fiber pickup by the refining bars, and then they are picked up by the edge of the bar and then transferred to the bar surface where the actual impact of refining is felt. And refining effects that are observed in fibers treated mechanically include fiber cutting, fine generation, external fibrillation, swelling. This is a picture of the valley beta. So we see that it has a bed plate that is fixed and has some kind of bars and grooves on it. The gap side can be adjusted manually by changing the refining load, and the effect of refining depends on the refining load and refining time. So for this study, the pulp consistency we'll be using is 2%, and the refining loads will be investigated will be 3 kg, 4.5 kg, and 5.5 kg. So the pulp is soaked overnight and then pulped for about 10 minutes before they are transferred to the valley beta for refining. This figure shows the evolution of the Shopper-Regler value, which is the extent of refining with refining time. And from this, we see that this shows a kind of kinetics of the refining process. And we see that with a lower refining load, the evolution of the fiber is slower. and faster at a higher refining load. So at the end, with this, in this project, we'll observe this effect of the kinetics of refining on the fiber development. This table presents the characteristics of the fiber before and after refining. So we see that the fiber lengths are reduced with refining, and also the WRV doubles after refining. So, but the most important results we obtained with the refining load of 4.5 kg. This is the same image. The effect of refining is apparent in this image as we see. So the cold caustic extraction was used for this study, and temperature concentration of soda studies were 20 gram per liter, 40, 60, and 100 gram per liter. The temperature of the study was 25 degrees Celsius, and pulp consistency was 5%. The enzymatic treatment was carried out with xylanase, and the temperature was 50 degrees, or reaction time 2 hours at consistency of 3%. So the performance of the xylan removal with refining and soda concentration was investigated. And we observe from this that the xylan content decreases with increasing soda concentration. And when we compare that with the refined pulp, so we see that the refining enhances the xylan removal process, so that a soda concentration of 100 gram per liter removes 50% more xylan in the refined pulp compared to the unrefined pulp. And also from this study, we see that soda concentration of 60 gram per liter and 100 gram per liter are interesting for further studies. We also investigated the effect of the refining on the xylanase treatment. So this is the evolution of the xylan content with increasing xylan dosage. We see that the xylan increases, the xylan removal is that we remove more xylan by increasing the xylan dosage. But when we apply refining prior to this enzymatic treatment, we improve the removal of the xylan from the pulp. So this is a positive result. So we also investigated the fines removal, in contribution of fines removal to the xylan extraction process from the paper pulp. And we used the Bauer magnet fiber classifier to fractionate the fibers from the fines. And for this study, fines were classified as particles of particle size less than or equal to 200 micrometers. So when we determine the sugar or the xylan content of the unrefined pulp, the refined pulp, and the fractionated fibers, we see that when we apply the fiber fractionation, we remove about 25% of the initial xylan content, which goes a long way in enhancing the removal of the xylan process from the pulp. So we see that the removal efficiency is higher for the pulp that is fractionated after refining before the cold caustic extraction process. In this study, we also investigated the effect of simultaneous refining and cold caustic extraction on the xylan removal. And we developed this approach in this study, and we saw that when we carry out simultaneous refining and cold caustic extraction at a lower soda concentration of 60 gram per liter, we're able to produce pulp that satisfy the xylan content required for dissolving application. So this is a very promising approach. We also investigated the evolution of degree of polymerization with refining and NOH concentration. And here we see that the refining process decreases the degree of polymerization of the pulp. And when we perform a fine fractionation, we slightly increase the degree of polymerization. So this shows that the fines contain lower molecular weight components that are removed during the fine fractionation process. We also looked at the degree of polymerization of the simultaneously refined simultaneous refining and cool caustic extraction sample, and we see it's also slightly lower. So this is advantageous in terms of reactivity, as the lower degree of polymerization enhances the reactivity of the pulp to derivatization dissolution. Also looked at the crystallinity index modification with refining. So we see that with refining, we decrease the crystallinity index, and when we apply a higher soda concentration of about 100 grams per liter, the crystallinity index even decreases further. So, and when we look at the cellulose 2 content, you see that the cellulose 2 content begins to form at a soda concentration of 10% in this study. So, meaning that the xylene extraction carried out at lower concentrations like 60 grams per liter do not form cellulose 2, and which is advantageous in terms of the reactivity, improving the reactivity of the pulp. So here we look at the molecular weight distribution of the reference pulp. We see two peaks. This represents the lower molecular weights components of the pulp, which is hemicellulose in this case. And then when we perform a simultaneous refining and cool caustic extraction, we see we eliminate the molecular weight peak. And then there's a slight shift from high molecular weight to low molecular weight of the pulp. So we see that this pulp treatment right here produces pulp that satisfies the dissolving pulp characteristics or condition. And other treatments we apply, like the fiber fractionation with 60 grams per liter, so that achieves also a narrow molecular weight distribution, which is also what we observe with when we treat the pulp with 100 grams per liter soda. So with refining, so these are interesting results. In conclusion, we see that valley beta refining increases accessibility, which is evident in the xylene removal, as a soda concentration of 100 grams per liter removes 50% more xylene from the refined pulp compared to unrefined pulp. Also, the new approaches to xylene removal introduced in this study show promising results, as we see whether we apply the refining first and perform a fractionation after, or a simultaneous treatment will produce pulp that satisfies dissolving pulp condition. So the prospects, we intend to evaluate the effect of the refining to improving the reactivity of the pulp in the terms of the viscous process, and we also intend to characterize the extracted xylene, see the effect of the refining on the properties of the xylene. I would like to thank my supervisors, my lab, my teammates, the Glyco Alp for the support, and for the co-doctoral for my funding. Thank you very much for listening.
Hello, everybody.
Hello.
So welcome to this production section. So I believe everyone is well. Before starting the question phase, I want to congratulate all the speakers by their excellent presentations and also remarkable work that was a base for their presentations. So congratulations for all of you.
Thank you.
So let's start the questions, and first question is for Margarida. So Margarida, nice to meet you.
Nice
when
to meet
you
you
start
too.
this sorption study, okay, when you start this sorption study, were you expecting to find these results, or are there any that seem unexpected to you?
Hello, everybody. I hope you are listening. I don't know if the sound is okay.
Yes,
it's okay?
yes.
Yes, share.
Well
Okay, thank you.
Okay.
Thank you. When we start the study, we are trying, let me say more clearly, that we are trying to improve the databases of the software in WinGEMS. And this is the purpose of this study. It's a very specific study, but the point is to get equilibrium data in order to improve the databases. And we noticed that there are some differences between the predictions and the observed values for some species concentrations. But the most important variable that we know that it is important, but we are aware to see that pH is really, really important, and the pH is not taken into account properly in the databases. So this is the main point here that I want to stress. Yeah. The pH,
okay. Thank you very much.
We shouldn't ignore the pH. Yeah.
Okay, thank you very much. It is clear. So, question for Claudia. And Claudia, a very interesting question. How to explain higher yields with high alkaline integration? When the start of cooking, when the findings of the modified cooking process indicate that lower and more uniform alkali profiles led to higher yield. So,
Hello, I hope you can hear me also.
yes.
Okay, modified cooking with lower alkali was proved to not be so good for impregnation process. The studies that have been done by modified cooking is more related with the viscosity and not by the yield. And in here, what we saw, and we want to
your
show
sound
you.
is not very good, Claudia.
Okay, I don't know. Now it's better. It's better now?
Yes, I can hear you.
I can
Yes,
hear
I
you.
can
Okay.
hear you.
So as I was saying, the modified cooking with lower alkali is not good for the impregnation step. And in this case that we presented, by increasing the alkali in the impregnation step, we are improving this process, and therefore we are getting a more homogeneous cooking afterwards. And that's the reason to get higher yield, because we are improving this homogeneity by the impregnation step improvement with a high alkali.
Claudia,
I
can you
hope I
repeat your
was
answer?
clear.
Because the first part, we could not understand you in the beginning.
Okay. So for modified cooking, what was seen was that lower alkali in impregnation step is not good. It will not help the impregnation. And the results that are in the literature is more related with the viscosity and not related with the yield. And what we saw here was the high alkali impregnation helps the impregnation, and therefore we will have a more uniform cooking. It was better now?
But there is not, yes, I understand, but there is not a risk of more severe attack to the hemicellulose in the first phase of the cooking process if the alkali level is higher than the reference.
No, what we saw was an increase in the glucomannane's content with this high alkali impregnation. And this is because by increasing this amount of alkali in this process, we are avoiding the peeling reaction in the glucomannanes. So therefore, we are increasing the yield because some way we are preserving them.
Okay, thank you very much. Question for Anna. Anna, I hope you are well. So, how can you explain that carboxylic group's content is important for capillarity and not for absorption? I were expecting the opposite.
Yes, this is something new for us when we saw it, because at the beginning, I will say that we consider the pentosanes and also the carboxylic groups more for the absorption than for the capillarity. However, we noticed that in the results, and we are looking for the statistics one,
the carboxylic groups as an importance here, but maybe could be, and we don't know that, and is one of the things that we can study in the future, could be the interaction, because we are talking about models when we are talking about statistics, and could be the interaction between the results of the fines, curls, etc. Not only the carboxylic groups per se alone, but the combination of it when we are talking about a model. I don't know if I explain myself in the right way.
Yes, I think so. Yes.
Okay.
Okay, thank you very much. So, question for Gloria. Gloria, can you tell us if the results you obtained from your study based on valley beta refining are notably different from those obtained with PFI mill refining?
Yes. For this study, in the case of the alkaline extraction, the difference was not so important because we had a removal degree of about 80% with the PFI and 84% with the valley beta. So it's not so different. But for the enzymatic treatment, the difference was noticeable because with the valley beta we had twice the removal activity we had for the PFI. And we attribute this to the large size of the enzymes and the large surface area that we produce with the valley beta refining. So I think it was the large surface area was more suited for the enzymatic activity with the valley beta.
Okay. Yes, I see. And can we consider simultaneous refining and cold caustic extraction as an innovation? So, is this something that has been studied in the past or not?
To the best of my knowledge, no. Yes, to the best of my knowledge, I haven't found any literature that has reported that. So I would say it's an innovation.
Okay, so congratulations. Cláudia, a lot of questions about sulfidity in both of the cooking process. So I believe that you have used the same craft parameters.
Yes, more or less the temperature is the same.
Cláudia, are you
and
listening?
the impregnation. Yes, are you listening to me?
So I will change to Anna. Anna, do you plan to extend the benchmark of your model to other species, such as softwood fibers?
It's not linked to the project because our project is related with eucalyptus. However, and take into account
we cannot listen to you, Cláudia. No.
Do you hear me?
No.
We are hearing you.
We are hearing, yeah.
So let's move to Anna. Anna, are you listening?
Yes.
So do you plan to extend the mark of your model to other wood species, such as softwood fibers?
Okay, as I'm saying, this work is linking to eucalyptus, and this part of the work only work with eucalyptus. However, and take into account the applicability of these models for industry, maybe we will start working with other species.
We lost you, Anna. Sorry. We didn't hear you in the last part.
Okay. I will repeat.
Yes, now you are reached.
Okay, so I'm saying that I hope and I desire to do such models for other species because we believe in this applicability for the industry.
Okay, and are you able to share your model?
Maybe if we sign like an NDA or something like that, maybe why not?
Okay, nice work. Thank you very much. Margarida, did you measure the calcium adsorption variation with time for a low pH, example pH 2? What is the time required to achieve a plateau for a certain low pH?
The kinetic of adsorption is normally fast. But yes, the low pH normally don't promote adsorption, but at high pH it occurs. So when we change from acidic stages to basic stages, it is necessary to take this into account, otherwise some deposits can occur.
Okay, thank you very much. Cláudia, let's see if I can listen to you now. Was that the potential of the pulp produced with this technique measured? Question about zeta potential.
No, it was not measured. Can you hear me?
Yes. And
okay.
And what have you compared results at the same sulfidity and using a typical impregnation stage? So I think that you have answered this question before.
No,
so,
I think you didn't. Okay.
No? Okay, so please go ahead.
Okay, I was saying that we use the same temperature, the same time of impregnation. However, to test this high alkali impregnation, we needed to start with a much higher sulfidity, because then we will do the dilution to make the right concentration for the cooking step. So for the cooking step, the sulfidities and the conditions are more or less the same, but in the impregnation, they are different.
Okay, thank you very much. Last question to Glória. How difficult is to filtrate this refined pulp at the end of the extraction?
It's quite difficult. It takes about 20 minutes to filter about 10 grams of the refined pulp, and it requires constant agitation. Perhaps it's really difficult because it had to be done manually. If we had an automated system, perhaps that difficulty would be overcome.
Okay, thank you very much. So one more question to let me see, Margarida. Based on the results, what would be your recommendations for the person responsible for the operation of the bleaching line? 30 seconds.
Yeah, it's the simulator has to, if you are predicting the precipitates based on simulator, the simulator must be improved. Otherwise, they don't predict well the occurrence of precipitates. You have to put equilibrium data in the software.
Okay, thank you. The valuable time has ended, so we have reached the end. I wish all of you great professional success. It was a pleasure to be with you.
Thank you.
Thank you so much. And
thank you very much.
Bye-bye.
Bye-bye. Thank you.
Bye.
Also.